Our next lesson will be on Chemical Nomenclature 2. The topics that we are going to cover in this lesson are going to be the numeric prefix system. We're going to talk a little bit about acids, and we're going to discuss hydrates. And so let's first talk about the numeric prefix system. The numeric prefix system is used in one of two cases. The first case is one where if you go through the nomenclature guide, as we discussed before, you notice that it starts off asking the question for the cation. Is the cation a metal? And so far, all the cations that we've used have been all metals. But if it's not a metal, then you have to go down through a series of steps. The next step is number 2, is the cation hydrogen. We'll talk about that in a second when we get to acids. But if the answer is no, if it's NH4, what if the answer is no? What if we get to step 4? That the cation is either a non-metal or a metalloid. Something like our cation is carbon or nitrogen or sulfur or phosphorus. And if you look at those, unlike all the other cations that we've used so far, is that these are generally almost always going to be multivalent. And if it is, then we're in number 4 here. We says the cation a metal or non-metalloid. It says go to number 12. And in number 12, it tells us that we can use one of two methods. That oxidation states can be indicated in one of two methods. The stock system can be used as if it was for some metals. So we could talk about something being, say, if you look at the possibility for sulfur. Sulfur, you could see, has a charge of +4 or +6 if you see it on your periodic table. And so if we had something like, for example, sulfur dioxide, SO2, we could call it sulfur dioxide. That's the most common name of it. But if we want to use the stock system, we'd say that, well, oxygen has a charge of -2. Sulfur, then, if there are two oxygens, would have to have a charge of +4. So we could say it's going to be sulfur 4 oxide. That's one option that we've got there. The other option is to use this numeric prefix system, in which case what we do is this goes on to number 13. And this is, if you look at it, it says an older system names the number of atoms of the element in one molecule of the compound using the prefixes di is 2, tri is 3, tetra is 4, penta is 5, hexa 6, hepta 7, octa 8, etc. It goes nona 9, deca 10. And so in this case what you do is you'd say, all right, if I'm using this, then if I have SO2, then I have 1 sulfur, but I have 2 oxygens. 2 is di, and so I'd say I have sulfur dioxide. And so this is one of the two ways that you use the numeric prefix system, just as a secondary way that you can use with certain nonmetals and metalloids. This is generally never used with metals as a cation, but certain nonmetals and metalloids as a cation to describe it. The second way is the way that's probably a little more difficult to understand. But so we're going to discuss this a little bit more. And this is what you have on your screen right now, is that it deals with something called empirical formula. Now, an empirical formula is basically the most reduced form of a formula. And we're going to see this a little bit more when we get to percent by mass later on here. But suppose that we have a case where you have a formula like we have on screen right here. We have N8O4. And so if you take a look at that N8O4, is that you see that we could reduce this. That we have 8 nitrogens, 4 oxygens, and if we were to reduce this, then we'd end up basically having N2O. Just like that. That N2O is basically what we call the empirical formula. And so this guy right here is going to be our empirical formula. And so that's the empirical formula of N8O4. It is the most reduced form. It does not properly describe the number of atoms in that molecule. That's one thing you have to sort of be clear on here. The empirical formula is simply the most reduced form, but it is not what the actual molecule is. So the empirical formula is N2O for this. The molecular formula is the one that's written here. It's N8O4. Is that whenever oftentimes we try to figure out what a molecule is, oftentimes if we're measuring something, we're measuring it by finding the ratio between two elements, we're going to come up with this empirical formula. But we really don't want that empirical formula. We want the molecular formula instead. And we'll talk about some techniques on how to find that later. But for right now is that what happens if you have something where you know that you have, let's say for example, like we have right here. Let's take a look at naming this N8O4. We could use, as it says, going through the method, we say that, okay, the cation here is nitrogen. Nitrogen is a nonmetal, so that takes number 4. It says the cation is a nonmetal. If so, go to number 12. And so if we were to go to number 12, then it says we could use the stock system. So let's take a look at using the stock system here. If we were to use the stock system in this, we'd say, all right, we know oxygen is going to have a valence of -2 And so since it's -2, there are 4 oxygens here. -2 times 4 is -8, like that. Nitrogen, on the other hand, we see it has, in order to balance this out, that we have 8 nitrogen, so each nitrogen must be +1. And so this would have to be, if we're going to write it out based on this, we'd say nitrogen, and in parentheses we do the Roman numeral 1, and it would be oxide. So we could write that out as one of our possibilities. But there's a problem with that. Nitrogen 1 oxide could just be, like we said before, N2O. That would be a perfectly good description of what nitrogen 1 oxide is. Or it could be this would be N4O2, or it could be N16O8. Whenever you have a molecule like N8O4 that can be reduced, that has an empirical formula that's different than the molecular formula itself, you cannot use this stock system to describe it, because of the fact that the stock system is only going to be able to describe the most simplified form, that empirical formula. And so instead, we have to use something else. And so this is where we're going to have to go ahead and use this prefix system. This is the only case where you have to use a numeric prefix system, is if you have a molecular formula that is different than that empirical formula. That is, you have a molecular formula that can be reduced. And so let's take a look at how we do that if we would just do this with our prefix system. So a prefix system here, we say that we went to number 12. We said in these compounds, oxidation states must always be indicated in one of 2 methods. We could use a stock system, but you say, oh, nope, can't use that. We have N8O4. That can be reduced. And since it can be reduced, we can't use the stock system. So we go to number 13. It said an older system names the number of atoms of the element in one molecule of the compound using the prefixes di equals 2, tri equals 3, tetra is 4, and so on and so forth. And so to do this right here, we say how many nitrogens and how many oxygens do we have here. And so basically, in this case, we know that we have 8 nitrogens. And so to do 8 nitrogens, we'd have to say that we're going to end up here with 8 is octa. So we start off with octa here. Then the next piece here is going to be nitrogen, right? So octanitrogen, and then the last part here for the cation is that, for the anion, back on the back here, we have 4 oxygens, and so we'd say the prefix for 4, if you look on there, 4 is tetra. Sort of like, in Tetris is the old game, you had to drop the blocks, and how many blocks were there in each piece? 4 blocks. Tetra is 4. So we have tetra oxide. Sometimes you will hear this as tetroxide. Both are proper forms. And so octanitrogen tetroxide would be a proper description of N8O4. In fact, really, this is just about the only way you could go out writing this out. And I forgot an O in nitrogen. Nitrogen. Right there. Let's take a look at our next one here. N3F6. And so in N3F6 is that what we're going to have to do is we say, can this be, we start off by going through and we say, is the cation a metal? Cation here is nitrogen, and we say nitrogen is not a metal, and so it can't be this. So we go on to number 2. Is the cation hydrogen? Nope, that's nitrogen, not hydrogen. Is it NH4? No, it's not that. So number 4. Is the cation a non-metal or metalloid? The answer is yes. The cation is a non-metal. Here it's nitrogen. So we go to number 12. We could use the stock system or we could use the numeric prefix system. But N3F6, is this reducible? Yes. Since it's reducible, it has an empirical formula. We're going to have to use the other system. We're going to have to use the numeric prefix system. So we go to 13. And in this older system is that basically we have to describe the numbers. So we have N3F6. 3 is tri. So we'd say this is going to be trinitrogen. And so we got trinitrogen for our first part. Our second part here is going to be the fluoride, the fluorine on the end. Since it is an anion, it's going to be fluoride. We have 6 of those. The prefix for 6 is hexa. So in this case, we would do hexoxide. And so trinitrogen hexoxide is what we're going to have for this particular formula right here. And so this is how you'd use the numeric prefix system. All right. Next topic up here is going to be on acids. So we skipped over one earlier when going through this. We were going through naming the cation, and we said the first one is, does the cation of metal go to 5? But the second one is, if the cation is hydrogen, go to number 9. Hydrogen is sort of special. Whenever you have a molecule that has hydrogen as the cation, then you normally have what's basically called an acid. This is the very definition of what an acid is. An acid is a molecule, is a chemical, where the cation in the molecule is hydrogen. And the only real exception to this is that acids are generally considered to be acids whenever they're dissolved in water. Technical term for this is in aqueous solution. And so if you have a molecule which is cation is hydrogen and it's an aqueous solution, it's always called an acid. Sometimes if it's dry, the hydrogen is treated like a metal, and it's using the same system we've been using before. But normally the rule is, if you got cation, it's hydrogen, it's almost always going to be an acid. And so going through this, we got to number 2. We said, is the cation hydrogen? And the answer for these acids, we say yes. So we go to number 9. And it says, as we said, compounds with H as their first element are generally named as acids, especially when in aqueous solutions. However, if they're dry, pure compounds, they may be named as if hydrogen were a metal. Go to number 5. So if we're assuming this is aqueous solution, the way of writing that out, if you ever do have something that's an aqueous solution, works sort of like this. If we have hydrochloric acid, HCl, if I wanted to show for certain this is an aqueous solution, what I would do is afterwards, in parentheses, I would put AQ. Anytime you see that AQ, that's what's called phase notation. When you put something in parentheses afterwards that's after the symbol like this, what it means, it tells you whether it's a solid, liquid, gas, or dissolved in water. And solid would be S, liquid would be L, gas would be G. AQ in parentheses means that it's going to be dissolved in water. And so this is how you'd write out aqueous solution. So this would definitely be an acid right here because it starts with hydrogen, that's its cation, and it's an aqueous solution. For the purposes of this class, unless I tell you it's a solid or a gas in that phase notation, assume any molecule that starts with hydrogen is going to be an acid. So, that being said, taking a look a little farther here, we jump down, as it says, to number, we're already on number 9, we finished this, so we go to number 10. So, the second part here, binary acids. If there are only, and this is number 10, if there are only 2 elements in the acid's formula, it is a binary acid, and its name is based solely on the non-hydrogen element. The key here, and the word here is the word binary, is the bi. Bi means 2, and so it only has 2 elements in it. And so, in this case, the name will start with hydro and end with a modified name of the other element. This example that we gave up here a little bit before, we talked about HCl. So the first part you say here is, okay, is that if I'm trying to name this, I know it starts with H. That means it's going to be an acid. And so I know it's going to be an acid right here for this guy right here. The second part we said is that since it's a binary acid, it only has H and it only has Cl, so only 2 parts to it. Then the name, as it says, will start with hydro and end with the modified name of the other element. And so we know this is going to start with hydro. Oftentimes people think that hydro means water. In this case, it does not. All the hydro means is that it is a binary acid. It's an acid that has hydrogen and only one other element. So we say hydro, and in this case right here, it ends with the modified name of the other element. The ending of the name of the other element is replaced with ic acid. So Cl is chlorine. So we drop the I-N-E and add ic acid. So we come up with hydrochloric acid. If I can fit it all in here. So hydrochloric, and that really didn't fit very well. It's hydrochloric acid. All right, that looks absolutely hideous, but this is basically what we end up with on here, is that when you name this out, you end up with hydrochloric acid. Okay? And so that would be a classic example of a binary acid. Another binary acid you might run across would be something like, let's suppose that we have H3N. In this case, is that we say, is this an acid? Yes. Cation is hydrogen, so we know it's an acid. Second question we say here is this binary? Yes, it only has 2 elements in it, hydrogen and nitrogen. And so it's a binary acid. We know it will start with hydro because of the fact that it's binary. And it'll end with a modified name of the other element. The other element here is nitrogen. And so we will drop off the gen and add ic acid. So in this case, this becomes hydronitric acid. And so hydronitric acid is what we have for this guy right here. So hydronitric acid, N-I-T-R-I-C acid, will be the name of H3N. So hydronitric acid. But suppose that we do not have something which has only 2 elements. We have something that has more than that. Like, for example, that what if we were given something along the lines of H3PO4? H3PO4. So we go through, we say, first thing is the cation hydrogen. Yes, most definitely hydrogen. And so that means it is going to be an acid here. And so then we go down and we say, does it have only 2 elements? This is number 10. If there are only 2 elements in the acid's formula, our answer is no. This has 3, hydrogen, phosphorus, and oxygen. It has a polyatomic ion. So we go to number 11. It says if the acid involves 3 elements, it's called a ternary acid. Tern is basically 3. Is basically the root that's there. And so it has 3 acids. It's called a ternary acid, and it's named for the polyatomic ion produced in the aqueous solution of the acid. Basically that it splits up. And so the key here when trying to understand ternary acids is we need to look at the polyatomic ion. In this case, it's PO4. Now, the way this works is if the name of the polyatomic ion ends in "ite," the acid will end in OUS acid, us acid. If it ends in "ate," it'll end in ic acid. And so we have to look at what PO4 is. And since it's a polyatomic ion, we look on our polyatomic ion sheet, and we see that PO4 is phosphate. Since this is phosphate, ends in ATE, we'll change the ending of phosphate, we'll drop the ate, and add ic acid. So this becomes phosphic acid or phosphoric acid. Either one works. So phosphoric acid. So phosphoric acid here, because of the fact that it has, as the root here, it has phosphate, and so because of the fact that it's 8, it's going to be ic acid. So the ic acid means it's 8, and then the phosphor comes from the first part of that PO4. And so at this point, you're done with the name. That's all you have to do. Let's try a couple more examples of this to get an idea of how this is going to work, just to get some practice on them. So let's name the following: H2SO4. So you start this out, first thing you should notice, you say, booyah, that's got an H out front. We know because of the fact that's there, this has to be an acid. And so we go through our acids, we say, is a cation hydrogen? Yes, go to 9. If it's got H for the first element, it's an acid. We already established that. We go to 10. Does this have 2 elements? H2SO4. No, it has 3. So it's not a binary acid. We're going to go on to number 11. If it involves 3 elements, it's ternary and is named for the polyatomic ion produced in the aqueous solution. So the question is, what is this polyatomic ion? What is SO4? And so to find what SO4 is, we say, let's first take a look. Let's look at our polyatomic ion sheet. Is this on here? And SO4, we look for that. Oh, yes, there it is. SO4 is sulfate. And so we have sulfate for this guy right here. And so we know you have sulfate. And so we have sulfate here. Now, what's going to happen is because of the fact that this is, it ends in 8, it tells us if the ion ends in 8, the acid will end in ic acid. And so what we're going to do is we're going to knock off the 8. We're going to add the ic acid to the end instead. And so as a result, our answer here is going to be sulfic or sulfuric. And either one I would accept here, acid. Okay? Technically, if you follow the rules, it probably would be just sulfic acid. But this is one of these that it's just traditionally been called sulfuric acid for the way we set this up. And so this would be what our answer would be. It's an acid because it starts with hydrogen. It is sulfuric because of the fact that it has sulfate. Drop the 8, add ic acid, and sulfuric acid. Our next one, HBr. Starts with hydrogen. It's an acid. Next question, does it have 2 elements or more than 2 elements? It has an H, it has a Br, that's 2 elements. And so as a result, this is going to be a binary acid. In binary acids, it says that the name is based solely on the non-hydrogen element, and the non-hydrogen element here is bromine. And so let's take a look at how we're going to change the bromine here. It says we're going to start off by starting the name with hydro. And so we know we're going to put hydro out front. We're going to add that to the front of the bromine going on here. The next thing we're going to do, it says that it will end with a modified name of the other element. The ending of the other element is replaced with ic acid. So we're going to drop the INE and add ic acid. And so as a result, this becomes, for our final answer, hydrobromic acid. So hydrobromic acid. And that's going to be the name of HBr. All right, let's take a look at our next one. HNO. It's clearly an acid, starts with hydrogen. Excuse me there. Starts with hydrogen, so we know it's an acid. Continuing on this right here is that we say, does it have two elements in it? Answer is no. HN and O, this is going to be a ternary acid. And for ternary acids, we say it's based only on the polyatomic ion. The polyatomic ion that's going to be here is NO. No. And we look at that on our polyatomic ion sheet. And is there an NO? We say, well, no. We do have, however, a nitrate. Nitrate's NO3. And so we say, well, NO is sort of similar to NO3. The only difference is it's lost 2 oxygen atoms. But we say, remember that. Remember back from our section that's on the anions that if you have a polyatomic ion which loses 2 oxygen atoms, that's going to be number 24. If the polyatomic ion contains 2 less oxygen atoms in the 8 form, then it's given a prefix of hypo before the name. And so in this case, it's not going to be nitrate. This is going to be hyponitrite, is going to be what NO would be. And so we'll write out hyponitrite would be the polyatomic ion name. And so we have hyponitrite, but then we got to turn this into an acid. And so if you look at the acid on back to number 12, or not 12, but number 11 again, where it talks about ternary acids, it says that the name of the polyatomic ion ends in ITE, ends in ite, then the acid will end in us acid. So we get rid of the ITE, and we're going to add OUS acid to the end. And so the name of this one will be hyponitrous acid. So hyponitrous, NITROUS acid. And so that would be the name of our particular HNO, hyponitrous acid. So that's how you go about naming acids and how you set that up. Our next topic is going to be on hydrates. Hydrates are generally not covered in your on your nomenclature guide. However, that whenever adding them, it really doesn't add too much complexity. Hydrates are basically cases where if you have a particular substance, when you have sort of a compound, that it's when it's in a dry form, is that oftentimes is that compounds will form crystals. And when they form crystals, it's not uncommon to have water molecules which are not attached to the molecule, but they do sort of sit inside the crystal. And so if you imagine a case of like a crystal that makes sort of like a pentagon shape, the way the atoms join together, is that you could imagine there might be a water molecule that sits in the middle. And so, you've got this case where, you got some crystallized thing, you got molecules on each of the vertices of this pentagon right here, and then somewhere sort of right in the middle here is our little water molecule. It sort of sits right there. And so that's sort of how that might work. So you can have sort of in hydrates, you have water. It's not attached to the molecule, but it's in with it. It sort of travels along with it. It's sort of, in a sense, sort of like a parasite. Not really, though. It doesn't really live off of the other molecules, but it's always with them in cases of hydrates. And that's why they call them hydrates. The key is hydra, water, right there. And so they contain water and other compound. The way you write out the formula for a hydrate is you write out the formula first. That's like our XXYY right here. And then you do a dot, and then you put NH2O, where N is the number of water molecules for every one molecule of the original compound. And so an example for the way this might work is that let's suppose that what we had here was we had a hydrate of table salt. This doesn't actually happen very often, but if you did, this is basically how it would work. We would say that we had NaCl, that's the formula of the compound, and then if we said that that there were 3 water molecules for every NaCl, we'd do a dot out after it, and then we would say 3H2O. Just like that. And so what this would show is this means that I have water that is basically mixed in, that is inside crystally, inside my salt here, my NaCl, my sodium chloride, and that for every 1 sodium chloride molecule, there are 3 water molecules. Now, note whenever you have hydrates are generally dry. The water is inside the crystal, and so it doesn't feel wet. It is possible to pull one out. We will find that soon enough. In fact, actually, that's the lab that we'll be doing here in just a little bit. But for what we've got right here is that this is sort of how this sets up, is that we have NaCl3H2O. The way you would pronounce this is you would first name the part that's down here, so NaCl. That's sodium chloride. And so you'd say sodium chloride, so that's our first name, compound name, and then you'd follow it by the prefix. The prefix here is 3. Remember that before we talked about the numeric prefixes, and the numeric prefix for 3 is tri. And so you would call this sodium chloride trihydrate. And so that's basically the way we set this up. So sodium chloride trihydrate would be NaCl.3H2O. That's how you'd pronounce it out. And so this is the way that basically hydrates work, is that you can either go back and forth, you're given a name for one, you can figure out the formula, or you're given a formula, you can figure out the name, and we'll take a look at some of these just right in here. So let's try some examples, just of general ones we talked about so far today. And so let's name the following compounds. We have COCl2.6H2O. Just what we talked about here. It's a hydrate. And so what we want to do is first we want to name the portion that's the normal molecule here, COCl2. And so we go through, we first start off with cobalt. We say, is cobalt a metal? We say, absolutely is cobalt a metal. It's either +2 or +3 for its valence, so we have to name the type. So we say it's cobalt is the first part. Since it could be either one, we have to look at chlorine. Chlorine is as an anion, so it has to be -1. And so it means the total for chlorine is -2. And that means this cobalt has to be +2. And so we know this is going to be cobalt 2, just like that. And then we got to name the last part, Cl2. That is, it's not polyatomic, so the second name just turns to ide. So this is Cl is chlorine, it becomes chloride. So we start off with cobalt 2 chloride. Now we have to name the second part, this 6H2O right here. We look at 6, that prefix on our numeric prefixes, 6 is hexa, and then the H2O is a hydrate, so hexahydrate. So cobalt 2 chloride hexahydrate would be this particular substance that we have here, COCl2.6H2O. Our next guy here, H3N. We start off by noting that this starts with H. That means it's going to be an acid. And so then we ask, we say we know it's an acid, we go through the steps, we say the next one asks, does it have 2 elements or more than that? Just 2 elements. It's a binary acid. Binary acids, we are, if you look at your nomenclature guide, you can see this is number 10 again. It says there are 2 acids in the acids formula. Its name is based only on the non-hydrogen element. It starts with hydro. That's going to be true if it's a binary acid automatically. And then it's going to continue with the rest of the other name here. So the other part here is nitrogen. So nitro, we won't finish it yet. We're not going to run it out here, because it says the ending of the name of the other element is replaced with ic acid. So instead of nitrogen, this becomes nitric acid. So our answer for this one, H3N, is hydronitric acid. All right, to our last one down here, Al2F6. We say, all right, we go through as the cation, we're going to go through, we say this, we look at this guy, we got Al2F6. We say, is this reducible? We say, oh, yes, it is. And so this has an empirical formula. That empirical formula is different than the molecular formula. We cannot just use the stock system for this then, because that would tell us something different. So because this is reducible, then it means we're going to have to use the numeric prefix system. And so to do that, basically what we're going to do here is we say Al2F6 is that fluorine, wait, what is this here? Aluminum has a valence of +3. Fluorine has a valence of -1. Is in this case, the general rule on these is that if you only have to put a prefix on one of the 2, you only put it on one of the 2. You only have to put it on both if there's some question about that it could be more than one possibility for both. In this case right here is the fluorine is, if I have 6 fluorines, aluminum can only be 2 aluminums. There's only one possibility because there's only one valence for aluminum. And so here, well, this would be, start off with here is going to be, I don't know why I just wrote a D, that should be an aluminum, it's an A. So aluminum. The second part here is it's going to be fluorine, but we have 6 fluorines, so the prefix for 6 is hexa. So hexafluoride, F-L-U-O-R-I-D-E, just like that. So our answer here would be Al2F6 is aluminum hexafluoride. Now let's try doing this backwards. What if we have to do it where we have the names and not the formulas? So find the formula for the following substances per nitric acid. So First thing, it's an acid. If it's an acid, what's that mean it starts with? We know this. Acid means hydrogen. So we know we've got a hydrogen to start this off. We can say that automatically just because of the fact that it is an acid. So we've got that there. Our next step is going to be, let's look at the name of this. If it's a binary acid, we know it starts with hydro. This doesn't start with hydro. Since it doesn't start with hydro, then we know it's going to be a polyatomic ion. So we got to look at this first part here. We know it's per nit something. The ic acid, we were told, if you look at the part on ternary acids, on number 11, it says it ends in ic acid if the ion ends in 8. And so basically what we want to do here is we are going to basically knock off the ic acid and add an 8 to the end to find out what the rest of this polyatomic ion is going to be. So it would be per nitrate. And so per nitrate, we figure out the same way as we did before. Nitrate's NO3. We know that from on the nomenclature guide from number 22, it says that if it has one more oxygen in the 8 form, it's given a prefix of per. And so that means this is one more oxygen than nitrate, which is NO3. So it means it's going to be NO4. And so we know we have NO4 right here. So NO4, we have to look at the valences. The valence of hydrogen is going to be +1. The valence of nitrate, or per nitrate, is going to be -1. And so these two are already balanced, and so our answer is just HNO4. That's how you'd write those out. Our next one, sodium carbonate dihydrate. The first step is going to be to name this first part of this molecule, the sodium carbonate right here. So sodium is Na. If we look at sodium on the periodic table, we see it only has one possible valence. That one possible valence is +1. And so we can just go ahead by starting off by saying we know this is going to be +1 for balancing reasons. The next part here is carbonate. Carbonate ends in ATE. That tells us it's going to be a polyatomic ion. We look on our polyatomic ion sheet, and guess what we find? We find that sure enough is that carbonate is on here. Carbonate is CO3. The valence on carbonate, looking at that, is -2. And so to balance this, we have +1 is sodium, -2 is carbonate. We have to have the same for both of them. So we know we're going to have twice as many sodiums. We have to have 2 sodiums. And so we have Na2CO3. And so this is the sodium carbonate part. The next part is the dihydrate. Remember to write the formula. You put a dot next. And then you want to write the prefix. The prefix is di. Di is 2. Hydrate means it's water, so H2O. And so here's our formula. Sodium carbonate dihydrate, Na2CO3.2H2O. Our very last one here is lithium trioxide. For lithium trioxide, here's sort of what we got. We know we're going to start off here with lithium. We know we've got that right here. The valence on lithium, looking that up, is going to be, should be +1, and so sure enough it's +1. And so we know lithium is +1 right here. The next one is oxygen. It's trioxide. And so the tri means there are 3 of them. And so we know that automatically, regardless of anything else, we have 3 oxygens here. And so that's going to be what forces it here, because everything always gets overridden by the fact that's tri. The tri takes over everything. And so we know there are 3 oxygens, period. Oxygen, though, has a valence of -2, right? And so if it's -2 for the valence of oxygen, but I have 3 of them, that means my total valence on that side is -6. That means I have to have +6 over here on the lithium side. If each lithium is +1, that means I have to have a total of 6 lithiums. And so my answer here is Li6O3, and that would be lithium trioxide. And that's how you work out problems that are like that.